This is a presentation of our paper Continual Transformers, redundancy-free attention for online inference. Online inference has been neglected. Most benchmarks in deep learning focus on the predictive performance and the offline case, for instance using full-time series clips as inputs. However, online processing producing in-time results is needed for many use cases such as live human monitoring and autonomous vehicles. But do we really need dedicated architectures, you might ask? Couldn't we just reuse offline models and use a sliding window? Here we would simply remove the last frame of the clip and append a new one to produce a new clip, which can be passed to the network in an identical manner. We could, but is it efficient? A dedicated architecture such as an RNN would be efficient. However, we know that other model architectures can give better results. Most of these are, however, forced to use a sliding window approach, which is inefficient. In this work, our goal is to transform the transformer encoder to perform sequential processing efficiently instead. Since transformers were proposed in 2017 by Vaswani and colleagues, they have taken the world by storm. There is virtually no task in machine learning where transformers haven't been used, with success in most applications and really pushing the state of the art in some. Consequently, the illustrations in this slide, which originally appeared in the Attention is All You Need paper, will be familiar to many of you. The transformer encoder takes as input a sequence of tokens, which is augmented by position encoding to induce positional bias. For each of n blocks, it mixes the tokens via multi-head self-attention, followed by the addition of a residual and a normalization layer. This is followed by a feed-forward layer with an additional residual and normalization again, before outputting the sequence of tokens. Multi-head attention itself takes 3 copies of the input, denoted as query, key, and value, and projects them linearly h times each before passing them to the scaled dot product attention, concatenating their channel dimensions and performing an element-wise linear projection again. Let's dive into the scaled product attention in more detail. The outer product of the scaled query and key matrices results in an n by n matrix of covariances between tokens. Scaling these with the row normalized softmax results in an attention matrix where an entry depends on all other entries in that row, i.e. the query token at hand, as well as on all key tokens. The attention is then used to aggregate entries across all tokens of the value matrix, which are summed up over the n entries of V for each dimension. The softmax normalization can be similarly expressed by first exponentiating the query key product and then normalizing by the row sum of entries. We are trying to optimize for the particular use case of continual inference, where each token corresponds to one time step and we assume that tokens will continually arrive. For each token, we want an updated output. But there is an issue. How can we efficiently compute the updated output when all SDA outputs depend on all tokens? This would be desirable given the big O of n squared d computation complexity of SDA. We have identified 2 cases of desired behavior for such a continual SDA. First, in the simple case, we could decide to only compute the output for the news token. In the second, more tricky case, we want to compute the prior outputs as well. The idea is to treat K and V as a first in first out queue, discarding the oldest token when we receive a new one. Then we only compute the attention A for a single query Q new and use it to aggregate cached value entries. This reduces the computation complexity markedly to only big O of ND. In the other case, we want to retroactively compute prior token outputs as well. Again, we treat query key and value matrices as first in first out queues. Then the idea is to add contributions from new tokens Q new, K new, and V new, while subtracting contributions from old tokens K old and V old, which have slided out of scope. First, we compute new entries of A as well as obsolete ones. Next, we use cached entries of the softmax row normalization vector DMM. These can be used to compute an updated set of prior entries. The newest entry is computed from scratch. Similarly, prior AV is cached as AVMem and updated based on the outer products of the newly computed entries of A and the new and old value tokens. The row corresponding to the newest value is computed from scratch again. Finally, the attention output is attained by normalizing AV with D. There is an exact computational correspondence between the attention computations. Specifically, the teeth output of the regular SDA is identical to the teeth output of the continual retroactive SDA, as well as the continual single output SDA result of the teeth query token, assuming the continual SDA observed identical prior tokens as were input to the regular SDA. In the presented figures, we see the flops per step and memory footprint for regular continual retroactive and continual single output SDAs at varying sequence length n and embedding dimension d. As seen in the top left figure, the linear computational complexity of SDA of n leads to significantly better scaling properties than for regular SDA. While the continual single output SDA generally has the lowest memory footprint as observed in the bottom row of figures, the retroactive SDA has lower memory consumption than the regular SDA when the embedding dimension d is smaller than the sequence length n. Continual transformer encoders, which have the same computational correspondence relations as the scaled dot product attentions, are structured in a near identical manner to their non-continual counterparts. The continual multi-head attention is computed by concatenating the outputs of h continual attention heads for the current query, key, and value vectors, and then performing a per token linear projection using an output weight. The continual transformer encoder first adds the result of the continual multi-head attention for the current input token x residually to the output. Here we use the notation of a selection function to note that only a single last token should be selected when the continual single output approach is used. The final output is given by token-wise projection with a two-layer feed-forward network. Since a transformer encoder does not provide positional bias, it is common to augment a token x sub I with a positional encoding p sub I. However, for regular transformers, the index I denotes a position in a sequence rather than a position in time. This poses an issue, since the last token at time t will be the next to last at time t plus 1 and thus in need of a different positional encoding. In effect, this means that each new input token step also changes the positional encoding of prior steps. As a solution, we propose to let the position be fixed in time rather than in sequence, and to recycle positional encodings when capital T steps have passed. In our ablation studies, we found this to be crucial for good performance during continual inference. Here we see the full continual transformer encoder architecture with recycling positional encoding and continual transformer encoder blocks. If a single transformer encoder block is desired, we recommend that one uses the continual single output transformer encoder for classification tasks and the continual retroactive transformer encoder for sequence-to-sequence tasks. For 2 blocks, one should first use the retroactive transformer encoder and the single output transformer encoder last. For 3 blocks or more, the same applies, but regular transformer encoders can be stacked in between. Due to the one-to-many nature of continual retroactive transformer encoders, their efficiency gains quickly diminish as more blocks are added. Consequently, we recommend the use of 1 or 2 block architectures. In our ablation studies, we found that class tokens were not necessary to achieve good performance. They can, however, be introduced after the first layer. In our experiments, we benchmarked our proposed 1 and 2 block transformer encoders against prior state-of-the-art methods for online action detection on TOOMS 14 and TV series, as well as on audio classification on GTZan. Using a simplified OAD transformer network, our online action detection experiments achieved a 60% reduction in floating point operations for 2 block transformer encoders without systematic loss in predictive performance. Similarly, our 1 block transformer encoder architectures were able to reduce flops by 98% per prediction compared to a regular 1 block transformer. In comparison with the original OAD transformer architecture, our 1 block continual transformer encoders reduce flops by 246 times on average, with less than 1% reduction in mean average precision. In conclusion, we propose two flavors of continual transformer encoder blocks, namely the continual single output transformer encoder and the continual retroactive transformer encoder. Moreover, we propose the use of recycling positional embeddings to accommodate progressive caching of positional information. The continual transformer encoders are extremely efficient when only a few blocks are used. Accordingly, we achieved a 63 times reduction in flops per prediction for 1-block architectures, as well as 2.6 times reductions for 2-block architectures, all without systematic reduction in predictive performance. Continual transformers are part of the Continual Inference Python package and can be readily downloaded today. Thanks for listening.